Hi everyone. Um, we are going back to week 6 because I realized that the video I uploaded didn't have the audio on. So here is with the audio on version. I really hope it gets captured now. So let me just double check everything. Uh, okay. So what we were doing, we're trying to understand what Euler method is. So essentially, if I give you a differential equation that looks like this with some initial condition, Euler's method will give you a so-called approximated curve to the actual curve of the solution. So remember that this is the initial value problem and this is the unique solution, right? So Euler's method will give you the graph that is very close to the graph of the unique solution. And how do you do it? Well, essentially, you choose a bunch of x coordinates known as t1, t2, t3, and so on. And these x coordinates have a fixed difference between them. And this fixed difference is delta t. And then you start getting your approximated value of y plus 1 depending on this thing. So we will understand this more precisely. So let's say we are trying to get the we are going to apply Euler's method to solve this differential equation with this initial value condition. So f ty here is 6y minus y squared. There is no t dependence. Okay. And the question is, how do I use this Euler's method? So first, see, this is the problem. The initial value is defined at 0 and the initial value is 1. So meaning your T0. So, okay, first of all, make this table, right? So make a column for Ti's, make the column of Yi. So what is Yi? So remember your function is Y, right? And Yt of 0 should be your actual value and Y of 0 is your approximated value. In other words, Yti is your actual value and Yi is the approximated value, which will be given to you by a formula. I will tell you and the formula is this one precisely. We'll see it very soon. So make a table for Ti, Yi, the derivative of the function y at Ti, which is, thanks to a differential equation, nothing but f of Ti, Yi, right? And then the slope, okay? So let's break it down one by one. So this is like, I mean, we have two more functions, dy dt and delta y. So that's what I mean. So let's break it down one by one. So y of 0 is 1, meaning t0 is this guy and y0 is this number. So just plug that thing in. So t0 is 0, y0 is 1. Now, what is f of t0, y0? See, you already have the formula for f of t of y, right? F of ty is the 6y minus y squared, right? So f of t0 y0 is nothing but 6y0 square minus y0 square, and you know the value of y0, right? So dy dt evaluated at t0, which is equal to f of t0 y0, is equal to 5. Okay, so the function dy dt at t0 is 5. And what about delta y? Delta y is just multiplying this guy by your common difference delta t. So here, as you can see, delta t is given to you to be 0.2. And if you do that, you will get delta y. The function delta y at t0 is this guy. Okay, so this is all how you should create the table. Now, this is just the first row. Our work is not done yet. Now, what does it represent geometrically? So geometrically, start with your initial point. This is t0, y0. Okay. Notice that this y0 is actually y of t0. Okay. By definition. Okay. So this point t0, y0 is indeed on your actual curve. So this point t0, y0 will be on your actual curve as well as the approximated curve. Okay. So this dotted line you are seeing, this is the actual curve, and this kind of collection of line you are seeing, these are your approximated curve. Well, to be honest, these lines are also imaginary. All you are getting are these points. But we are like trying to connect these points to show you how the curve, the approximated curve looks like. Anyway, so t0, y0, as you can see, is 0, comma 1. And this is your initial point. Now, this to then make sense geometrically. The question is, what does this value and this value mean? Very easy. So what Euler's method does is the following. What is dy dt at t0? Try to think. Dy dt at t0 is nothing but the slope of the tangent drawn to the actual curve of y at t0. Meaning, if you believe this dotted line to be the actual curve, and if you try to draw the tangent at t0, y0, right? The slope of this tangent is given to you to be dy dt at t0, right? Makes sense? So what Euler is saying that, okay, so the tangent line is a line from this point t0, y0 with slope dy dt at t equals to t0. So let's say, okay, instead of going along with the actual curve, which we do not know how it looks like, let us just go from this point, maintaining the slope dy dt at t0 in its direction, right? So let's go maybe this way. Okay, does it sound good? So here dy dt is 5. So maybe the tangent looks like this, right? So what I did, I started from t0, y0. I drew the tangent line from this point with slope 5. And how far did we go? I went this delta t amount in the x-axis. So that is where delta t is coming. So what delta t is doing is delta t is telling you exactly at what distance or like how far these points on the x-axis are sitting from each other. So this is t0, this is t0 plus delta t, which is t1. This is t0 plus 2 delta t, which is t2, and so on. Okay, we're not okay. So the first row just tells you to get started with the process. The second row will tell you the next point, the t1, y1. I mean this point. So what is t1? T1 is t0 plus delta t. What is y1? Y1 is y0 plus delta y0. So this guy. Remember, like, so yeah. So remember this thing. Yi is yi minus 1 plus delta y. So I should be more careful here. Delta y of or which the textbook will say just delta I. Okay. So delta y is nothing but this guy. Delta y of ti is nothing but this guy. Okay. So let's go back to the table. So T1 is this guy plus delta T. Y1 is this guy plus delta Y. I mean, just take this and add it up. You will get Y1. What is dy dt at Y1? Just evaluate the function f of t of y at this point at T1 and Y1, right? So this is So T1 is 0.2, Y1 is 2. Evaluate the function at T1, Y1, 0.2, comma 2. So that will give you the dy dt at T1. So I made a typo here. No, damn. Okay. Then again find out delta y T1, which is this guy multiplied to delta T, right? Which is this. And then to get y2, so what is your approximated point? Your approximated point is T1, Y1. So T1, Y1. That is your next approximated point. For T2, Y2, what should you do? Well, T2 is T1 plus delta T, right? So just add delta T to this guy. Y3 is Y2 plus delta Y. So just add delta Y, I mean add this and this, right? That would give you Y2. Then evaluate this T2 and Y2 at F T2, Y2, that would give you the slope. And then finally, this one is just this guy multiplied to delta T. So just remember this thing, column. So say so this is column 1, which is the column of T, column 2, this is the column of Y, column 3, so this is the column of FYYY, and this is column 4. So just to remind you what these are, this is like T, Ti, Yi, f of Ti, Yi, and this is delta Y, Ti. Okay. So say this is so this is ith row, or maybe jth row, jth row, right? Okay. Then what is this j plus 1th row? My bad. So this is jth row plus delta t, right? Meaning to get T2, you just add delta T to this guy and you will get it, right? This is jth row of column 2 plus jth row of column 4, right? So just add this and this to get this. Okay, sounds good. So maybe I should make an arrow. Okay, what about this guy? F of these two guys, right? F of these two guys. Right? So evaluate F at, so this is your so-called Tj plus 1, and this is your Yj plus 1. So this is F of Tj plus 1 comma Yj plus 1, right? And finally, what about this guy? This is column 3 of row j plus 1, meaning this guy times delta t. So just multiply this guy by delta t to get this guy. So let me also make a note. So all these arrows tells you the dependence of what rows and what columns gives you the next row and next column. Okay. Okay. Also with this, so what is this TIs, YIs? These are like approximated points. So you keep plotting T1, Y1, T2, Y2, T3, Y3. These will give you the approximated points. And then you join them by this line to show you that how the curve looks like discretely. Okay, also there is something called error in Euler's method. So what is that? So suppose you know the exact value of the curve at a point t bar, then what is this error? The error is y t bar minus y delta t. So suppose what I want to mean is this. So suppose this is the point t bar at which you know the exact value, the actual value of the function, right? Now, suppose you start doing your Euler's method from t0, choose, sorry, let me just draw a picture. So you know the actual value. Now you're trying to approximate the value yt bar using Euler's method. How are you doing it? So choose a t0, fix a t0, and then choose a delta t, right? And then for this chosen delta t, use the Euler's method, right? That would give you some approximated, I mean, you have to first divide, sorry, like divide this distance of t bar minus t0 by some number, right? And that is your delta t. And then using that, try to approximate the value. So say t bar is t, I don't know, n. Then what you get using Euler's method is t bar equals to tn yn, right? So this is your so-called y of delta t, right? So you get an approximated value at t bar. So the difference is called the error. Okay. Now, why is this like varying? Because you can vary this delta t, right? You can choose a smaller delta t and still do the Euler's method and you get a different error. To be honest, the more you make delta t smaller, the better approximation you will get. That's it. So that's all about Euler's method. And finally, you have something called separable equation. What is separable equation? Well, this is one of the most brilliant ways of solving differential equation. So, and how do you solve it? You solve it by separating the variables. Meaning, suppose I'm trying to solve this equation, right? There are a bunch of t's and y's involved here. What should I do? Bring all the y together and bring all the t together, right? So write down the differential equation in this way. Now bring y here and bring the t's here. So you get something like this. And once you get that, do the indefinite integration and you get this. And also you will definitely get something called this integration constant. Do not forget it. So now then try to solve it using log and whatever, and you ultimately will get something like this. Okay, so this is called separation of variable. Also note that there are infinite many solution because this C1 can be any real number coming from the integration constant, right? So have a look at this. Now, okay, this can also be initial value problem, meaning that let's try to solve this equation. Again, separate all the y's and separate all the t's, bring all the y's together, bring all the t's together, you will get something like this. Integrate, you will get log y log t square plus 1 and blah blah blah. Whenever you see log, try to remove it from picture by taking exponential. So take e power log y and e power this entire thing. Then it will become, okay, e power log y is y always, or mod y. Okay, sorry, e power log y is y. Keep this in mind all the time. Okay. And okay, let me just make a separate note. Integration 1 over y dy is log mod y, not y. And e power log x is x. So these are like two things you should remember. So do that to find out the value of y. And then your solution without invoking the initial condition is this guy. So again, you have infinitely many solution, but now you have an initial value, right? So there will be just one solution. So one particular value of C1 will satisfy it. So plug in t equals to 0 and solve for C1 and you will get the value of C1. Okay. So I will upload everything. I hope you look at this supplementary lecture videos. They do much better job than me. So that's it. Thank you.